Welcome to another presentation in the series Electronics, the Story of One Human Lifetime, presented by David Beams and Gary James. I am David Beams, Associate Professor Emeritus of Electrical Engineering, and I am your presenter and raconteur this afternoon. Before we get started, just a note to our loyal viewers, all 5 or 6 of you, who've been wondering where the good and erudite Mr. James has been. I have some good news for you. I recently saw him in Illinois, and he is doing well and continuing to be a productive member of society as a graphic designer. For me, I'm just a little past 5 years in retirement, and I can't say that I'm a productive member of society. In fact, I consider myself more of a social parasite, but I've adapted to it. Anyway, today's presentation is Resources for Amplifier Circuits, Part 2, a sequel to, wait for it, Resources for Amplifier Circuits, Part 1, which you can already find on YouTube. So, the new resources that I'm announcing that are available for download and available for your use are as follows. Under tutorials and notes, I have notes on the source follower, high frequency behavior of the source follower circuit, small signal analysis of the MOS differential pair with a common source output stage. I have the output resistance, calculation of the output resistance of the actively loaded differential pair, NMOS differential pair drain current versus differential input voltage, and a common source amplifier's cutoff frequency estimated by 2 different methods, one using the Miller effect and the second, the open circuit time constant method. And we have common gate and common base amplifier output resistance calculations, common gate amplifier input resistance, common gate amplifier voltage gain and input and output resistances, common drain amplifier small signal model and high frequency behavior, common drain amplifier analysis, and common base amplifier voltage gain. You'll notice that from the names of some of these tutorials and notes that there's some significant overlap in the subject material. That's because they were created at various times in kind of an ad hoc manner as I needed them as teaching materials. And so, yeah, there was a distinct lack of overall planning in their development. So there is some overlap, but that's all right. Oh, there we go. All right, so we also have 4 Excel spreadsheets for you. One is calculations of a 4-transistor FET bias generator circuit. I'll show you that in a minute. Feedback amplifier analysis. We have high-frequency small signal analysis of basic amplifier circuits, and finally, DC and AC analysis of the BJT Wilson current mirror. So let's take a quick look at some of these, or let's take a quick look at these spreadsheets and see what they can do for you. Here is the spreadsheet for the 4-transistor bias current generator. It consists of 2 current mirrors. A current mirror is a pair of matched PMOS transistors, and an asymmetric current mirror of 2 NMOS transistors. If you look carefully, you'll see that the width to length ratio of transistor 1 is much larger than the width to length ratio of transistor 2. The larger width to length ratio of transistor 1 means that, compared to 2, means that for the same drain current in each, the gate to source voltage across M1 will be smaller than the gate to source voltage across MOSFET M2. And you also see that the gate to source voltage of 2 equals the gate to source voltage of 1 plus the voltage drop across the resistor. The voltage drop across the resistor, of course, is the drain current multiplied by the resistance. So we have calculations here that calculate the calculate both the gate to source voltage of MOSFET 2, the gate to source voltage of MOSFET 1, and the voltage across the resistor as a function of the drain current. And if we have found a solution in which both drain currents of MOSFET 1 and MOSFET 2 are equal, then VGS2 equals VGS1 plus the voltage across the resistor. So you can play with the numbers here. For example, with a resistance of about 1500 ohms and the parameters that I've entered. Here are the width to length ratios of transistors 1 and 2. Here's the process transconductance parameter of the two NMOS transistors, 1500 ohms for the source resistor. And with a drain current of about 555 microamps, the sum of VGS2 and VGS2 is approximately equal, very close to the sum of VGS1 and the voltage across the resistor. Now, there is a second calculation built into this spreadsheet, and that is I have drawn a graph here, calculated and drawn a graph of the voltage across the resistor minus the difference in the gate to source voltages as a function of drain current. That's what these calculations are here. So you can solve for the drain current that would flow in M1 and M2 by just simply using these calculations above, maybe trial and error, change the value of the drain current. Or if you want to get an idea where the solution lies, you can look at this graph of V sub R minus delta VGS versus, as the independent variable, the drain current. And you'll notice that there are 2 points where VR minus delta VGS passes through 0. One is at a drain current of 0, not terribly useful. And then there is another one at another positive value. So here we see that at somewhere around 550, just a little over 550 microamperes, this curve passes through 0 again. Okay. Let's change the resistance. Let's go to 2000 ohms. And we obviously no longer have VGS2 equals VGS1 plus V sub R. But let's see. This graph tells me that around 310 or so microamperes that this quantity passes through 0. So let's try 310. And yeah, that's very close. Okay. So that's how you use the resources in this particular spreadsheet. This is the spreadsheet that is the analysis of feedback amplifiers of various kinds. Feedback amplifiers built around an operational amplifier. Block here is representing an operational amplifier whose model is a voltage-controlled voltage source with a given open-loop voltage gain in series with an output resistance and having a differential input resistance. This block are those parameters of the op-amp. The external circuit components, in this case, a load resistor and 2 resistors R sub F and R in. And from the parameters you enter, it calculates the circuit performance. Here's the closed loop voltage gain, volts per volt. The input resistance is seen by the input signal source, and the output resistance of the voltage amplifier with those parameters computed from the formulas that you see here. The second tab is of a transresistance amplifier. That is current in, voltage out, model of the operational amplifier, external circuit components, and the calculated performance, the transresistance, the input resistance, and the output resistance. Next tab is the transconductance amplifier. It is voltage in, current out, op-amp parameters, external circuit components, computed closed loop transconductance, the input and output resistances. And finally, the fourth one is a current amplifier. And again, op-amp parameters, external circuit components, computed performance, and the equations from which the performance are calculated. Here we have the spreadsheet of small signal high frequency amplifier analysis, different types of amplifier circuits, for each one having its own worksheet tab. This first one is the common source amplifier. And here we have user supplied parameters, gate to source capacitance, gate to drain capacitance, the signal source resistance of the signal source, the drain resistor, the load resistor, the output resistance or drain to source resistance of the MOSFET transconductance, so forth. And it calculates for you two different transfer relationships. One is the voltage gain of output voltage to the open circuit generator voltage, which we call AVS here, V out to V signal. And it gives me here a mid-band voltage gain, and it gives the locations of 2 poles and 1 0 in the transfer relationship of this amplifier, in this transfer function. And there's a second transfer function, which is the voltage, the gain output voltage with respect to the input voltage. It calculates the mid-band value and the location on the complexes plane of the pole and 0 and the associated break frequencies. And we have on the second tab, we have the common gate amplifier, where we have, again, the device and circuit parameters, user supplied values. And it calculates 2 transfer functions. That is, one is for the output voltage with respect to the open circuit generator voltage, and the other is the output voltage with respect to the input voltage of the amplifier. And again, it calculates the mid-band voltage gain and the locations of 2 poles for both transfer relationships. Then the third one, the third tab is for the emitter follower. And the fourth tab is some instructions in how to apply the preceding models to different circumstances. For instance, how to analyze the common emitter amplifier using the common source amplifier worksheet, how to analyze the common base amplifier using the common gate amplifier worksheet, and how to analyze a source follower using the emitter follower tab of this spreadsheet. And the fourth one is this worksheet, which is DC and AC analysis of the BJT Wilson current mirror circuit. The models are on this tab. This is the circuit diagram, the external controlling voltage is VDC, and this bias setting resistor R sub B, and VODC sets the output voltage that the current mirror is operating into. This is the small signal model of the circuit. And again, user supplied information are in the tan cells, and results. Here's the DC output current with the given values. And here is the calculated output resistance of the current mirror. And here are the formulas for the current. And here is the output conductance of the current mirror. Anyway, so that wraps up the 4 worksheets, or the 4 Excel worksheets that are part of this presentation. And we have one LTSpice circuit as part of this presentation. We have an LTSpice simulation of the 4-transistor FET bias circuit. Well, let's take a quick look at that. Here is the LTSpice model of the 4-transistor bias generator circuit. And you have a choice here of either Cedra and Smith models for the MOSFETs or Rizavi's models for the MOSFET PNN channel devices. One difference between this circuit and the spreadsheet one that is the basis of the spreadsheet, is that I have here this 1 nanoampere source that I've added to make certain that the circuit cannot find a solution at a DC, at quiescent, a DC current of 0. It forces the only solution that this circuit can find to be an active one, not 0 current. Let's run it here, and okay, there we go. It has run, and we can see that, let's pull this out of the way. M3 and M4 are the NMOS devices. The drain current of M3 is 62.16 microamperes, and the drain current of M4 is 58.001. Very close match. Now, the spreadsheet, of course, did not take into account the output resistance of each of the MOSFETs, the channel length modulation effects. This, of course, does indeed do that. The LTSpice simulation does. Anyway, present all these resources for your use. Just remember, what you see is what you get. And that's probably the most useful engineering acronym since keep it simple, stupid, or KISS. So putting the wraps on everything, remember, the link to these resources is in the video description. And if you find any of these resources useful, by all means, let us know, leave a comment. So we ask you to keep those cards and letters coming and let us know that our work is appreciated. My name is David Beams. It has been my privilege to be your presenter this afternoon, and I hope to see you again soon in another presentation of Electronics, the Story of One Human Lifetime.